Okay, everyone. With chapter 21 here, we're going to sort of shift gears a little bit away from what we've been talking about for the past few chapters with, z-scores and t-tests and that sort of thing. Um, Today, we're going to introduce in chapter 21 what's called the chi-square test for goodness of fit. Now, this is still statistical inference, so we are still, formulating a null hypothesis and an alternative hypothesis. We are, based on our data, calculating rather some sort of test statistic, like the z-test we did before, or the z-score, and the t calculation we did before. But we're going to compare that test statistic to a table to find a p-value, and then based on that, we will either accept or reject our null hypothesis. But the chi-square test for goodness of fit is basically going to be used for looking at proportional data. Okay, so and again, here's the outline for the chapter that I always show at the beginning of these. What the chi-square test is going to allow us to do is look at observed proportions and compare those to expected proportions. And if we see any differences, which typically we will, we're going to look to see if those differences are significant, statistically significant, now knowing what that means. All right, so we use this chi-square test. By the way, this is the Greek symbol for it, okay, the Greek letter chi. So we use the chi-square test for categorical data. And remember, categorical data is data that is grouped into categories. Like, for example, if you look down here, what we have are number of births for each day of the week, or proportion of births for each day of the week. So we have 7 different categories. Each day of the week is a category, and we have a number of data points or values lumped into each of those 7 days of the week in terms of number of births or proportion of births that occur for those days of the week. This is categorical data. So what the chi-square test is going to do is it's going to measure how different the observed data are from what we expect if the null hypothesis is true. So take a look at this data set here, for example, the bottom left, or actually look at the bottom right figure. So we have a data set of 700 births, and I actually think this is for an Australian city. I don't know over what time period this would have been necessarily, but if you have some number of births and everything is at random, there wouldn't be any reason to expect that you would get more or less births on any given day of the week. So our null hypothesis here would be that the proportions of births, say, on a Monday should be the same as the proportion of births on Tuesday, as on Wednesday, as on Thursday, and so on down the line. So in other words, we should have the same proportion of births on each day of the week. And any given day of the week should have 1/7 of the total number of births. That would be our null hypothesis. This would be what we expect under the null hypothesis, okay, these proportions. But we look at the real data, the actual data, which you see here in this figure, and you can see that the proportion of births does vary. You have the highest proportion of births on Tuesday, the lowest on a Saturday. So what the chi-square test is going to do is compare these observed values or proportions to what we expect, and it's going to help us figure out if those differences are statistically significant. In other words, if there's something interesting going on, or if the differences that we see here are nothing more than random variation, okay? For example, it could be that an obstetrician doesn't want to work on Saturday and Sunday, doesn't want to work on weekends. So if they know that they have some of their patients whose due dates are on the weekends, they might go ahead and do some on a Friday and get it over with, right? That could be something that's causing these low birth rates on Saturday and Sunday that you see in this figure. But the chi-square test is going to allow us to look and see if that is likely what's going on, all right? Okay, so the chi-square calculation is really simple, all right? So again, it's going to compare observed and expected counts, okay? The observed counts are what we actually see in our data, right? It's the actual number of observations that fit into each category, okay? The expected counts are those observations, or the proportion of observations we would expect to see if our null hypothesis is true. So let me fill this in here. So our chi-square statistic equals the sum of the observed counts minus the expected counts squared divided by the expected counts. So you take your observed count, say actual number of births on a Monday, let's say, subtract from that the expected number of births on a Monday, and you square that and divide by the expected count. So we just did this for a Monday, but you would also need to do it for every other day of the week. So you would actually end up getting a total of 7 of these calculations, 1 for each day of the week. Then our summation sign says to add up all 7 of those. And that sum total is going to be our chi-square statistic. All right, that's our test statistic. We look at that chi-square statistic on a table, table D, as we'll see in a minute, and it's going to basically tell us what the p-value is. All right, so the idea here is that large values of the chi-square statistic are usually going to indicate that we have some fairly significant or large deviations, I should say, from the expected distribution under our null hypothesis. Large values of a chi-square statistic should give us small p-values, which are likely to be statistically significant. All right, so let's look at the chi-square distribution a little bit. So we have an entire family of distributions here that are based on that differ based on their degrees of freedom. And again, degrees of freedom is sort of an estimate of sample size, okay, or it's related to sample size. We'll see how to calculate that here in a minute for chi-square. So the thing about the chi-square distribution is that they're always positive, so they're always 0 or greater, centered on 0 or greater, and we never have any negative numbers. And this is because the way that we calculate it, we're squaring, right? And the squaring that we do for the difference between the observed and expected counts is just a way to get rid of negative numbers. So that's why our distributions are always positive. They're always on the right hand side of 0, okay? All right, they take on positive values, and another thing about the chi-square statistic distributions is that they're always skewed to the right, as you see here in this figure. Okay, and the amount of skew depends on the sample size and all that, as we've seen before. Okay, that's just some unique features of the chi-square distribution. Let's look at our table. So this is table D, and this should be in the handout I gave you guys. So for table D, what we have to do is find the appropriate row on the left, and that's our degrees of freedom, okay? And for our example with the number of births per week, we have a degrees of freedom of 6. So we calculated a chi-square statistic. Well, we didn't actually do that, but this is the chi-square statistic for that data, 15.9, and I can tell you it's a pretty large chi-square. We go down our degrees of freedom row of 6, and we find where 15.9 falls, and it falls between these two values here. Go up to your p-value row, and you see our p-value then is between 0.01 and 0.02. That tells us that the differences we saw in terms of proportion of births on any given day of the week compared to what we expect, those differences are significant. They're statistically significant. So maybe you do have a guy, or an obstetrician rather, who doesn't want to work on the weekends, so he or she induces their patients who have due dates on the weekends, and maybe you see a larger number on Friday or whatever. Okay. So, goodness of fit hypotheses, right? So we have to develop hypotheses here, null and alternative, just like we've done for any other tests in the case of statistical inference. So we're using the chi-square test again for categorical variables, okay? We have a single random sample with any number of levels, any number of k levels, all right? With the births for each day of the week, the number of levels was 7, 1 for each day of the week, okay? The null hypothesis here in the chi-square could be simply that all population proportions are equal. That's a uniform hypothesis, and that's actually what we saw in the case of our births example. That's one possibility, a uniform hypothesis, or we could have a situation where the proportions are equal to some specific values that we know in advance, okay? But again, this has to be as long as the sum of all the population proportions equals 1. They have to add up to 1, all right? So one thing that chi-square analysis is very often used for is in genetics, looking at the actual proportions of offspring with certain phenotypes compared to those that we expect to get based on a, let's say, a Mendelian genetic model. All right. So as an example, let's say we're crossing homozygote parents expressing two codominant phenotypes. Okay. We would expect in the F2 to get the proportion of A phenotypes to be 1/4, AB phenotypes to be 1/2, and B phenotypes to be 1/4. So the reason for that, we'll draw over here, is this. We do our Punnett square. So we have one parent's gamete genotypes on the top and the other parent's gamete genotypes on the bottom, or on the side. If these two gametes fuse during fertilization, you get an individual with an A phenotype. This one gives you an AB phenotype, as does this one, and then this one gives you a B phenotype. So we have 1/4 A, 1/2 AB, and 1/4 B. So those are our expected phenotype proportions under a Mendelian model. All right. So this is again why chi-square is very often used for this kind of genetic analysis. Okay. So for a random sample of a given size with a certain number of levels of a categorical variable, whenever we're testing the null hypothesis that the proportions for each level are all even or equal, in other words, a uniform distribution, the expected counts are going to be our sample size divided by the number of levels. So with the births example, we had 700 births. We had 7 days for each week in a week. And so we have 700 divided by 7. You would expect to have 100 births per day, or 1/7 of the births on any given day. That's what this means as a uniform distribution. All right. So what kind of conditions have to be met for the chi-square goodness of fit test to be useful? In other words, what sort of criteria do our data have to meet? Okay, well, this is pretty simple. There are really only two. And first of all, obviously, we have to have a random sample. That's always going to be the case. Secondly, all expected counts have to have values greater than or equal to 1. All right. Finally, no more than 1/5 or 20% of the expected counts can have values less than 5. So as long as our data meet these two requirements and we have a random sample, we can use chi-square analysis on that data. So let's look at an example. All right. So aphids are insects. Aphids evade predators, ladybugs, by dropping off the leaf. An experiment examined the mechanism of aphid drops. When dropped upside down from delicate tweezers, live aphids landed on their ventral side in 95% of the trials, 19 out of 20. In contrast, dead aphids landed on their ventral side 52.2% of the trials, 12 out of 23. So a dead aphid seems to be sort of behaving like a coin toss, right? Half the time it lands on its ventral side, half the time on its dorsal side. Okay. So the question is there evidence at a significance level of 5%, in other words, a 95% confidence level, that live aphids landing right side up on their ventral side, in other words, on their feet, is not a chance event? In other words, are aphids controlling their landing? Okay, so our null hypothesis is that the probability of ventral landings equals 0.5, and the probability or proportion of dorsal landings also equals 0.5, just like flipping a coin. The alternative with the case of chi-square is really simple. It just says that the null hypothesis is not true. That's always what your alternative hypothesis in the case of chi-square says. It says that your null simply is not true. All right. So let me fill this in again. So iPad, gotta love it. Okay. Not done. Okay, so we have our data right here, our data table. We have observed counts, total of 20. 19 of them, we had aphids landing on their feet, on their ventral side. In one of them, it landed on its back, on its dorsal side. The expected count under our null hypothesis is that 50% of the landings should be dorsal and 50% should be ventral, so 0.5. So we need to find our expected counts, okay? So we have a total sample size of 20, and if you divide that by 2, because there's 2 ways they can land, that gives you 10. Another way to do it is to multiply 20 by the expected proportion, 0.5, that gives you 10, and that gives you 10. So we expect 10 of each on average. All right, now we need to look at what's called our contributions. So we need to do this calculation for each of the two possibilities, okay? So our first one, we have observed minus expected. So look down here, observed minus expected squared divided by expected. So 19 minus 10, observed minus expected squared divided by expected of 10 gives you what's called a contribution of 8.1. 8.1. We also need to do that for the one that landed on its back, on its dorsal side. So again, observed was 1 minus expected of 10 squared divided by expected of 10, again gives us 8.1. The reason why these two contribution values are the same is because we have the same distance between our actual values and expected, observed and expected. We have a difference of 9 here, difference of 9 there. That's why we get the same value. And again, these two values, okay, are referred to as contributions. So we have to add those two contributions together because that's what our summation sign says. We add those together and we get a chi-square of 16.2. That's a pretty large chi-square, all right, as chi-squares go. So let's look at our result here. So again, when dropped upside down from delicate tweezers, live aphids land on their ventral side in 95% of the trials, 19 out of 20. So our question here is this evidence at 95% confidence that live aphids actually control their landing? Kind of like cats, they land on their feet, right? Is this evidence of that? Well, we have our null hypothesis saying the proportion of landings on ventral and dorsal should be equal. The alternative simply says that's not true. Well, we know that we've calculated a chi-square of 16.2. So we have a degrees of freedom of 1, okay? And I may have forgot to mention this before, but our degrees of freedom is simply, so df, degrees of freedom, equals number of levels minus 1. K is your number of levels minus 1. We have 2 levels in this example. An aphid can land on its ventral side or its dorsal side. So 2 minus 1 is 1 degrees of freedom. And so we look at the first row of our table for degrees of freedom of 1. We go over until we find 16.2, and we see it's not there. 16.2 is way over here somewhere. So notice our p-values get smaller as we go to the right. This means all we can say from the table is that our p-value is less than 0.0005 because that's our last p-value right there. If you run this through software like Minitab, it calculates the p-value more precisely, 0.00006. That is very highly significant, so we reject our null here. This p-value of 0.006 means there's a 0.0006 means that in percentage terms, there's a 0.006% chance of 20 aphids being dropped and only one of them landing on its back if our null hypothesis is true. The chance of that is so remote, we reject our null hypothesis in favor of the alternative, which is going to basically say that aphids do apparently control their landing. So we have found very strong evidence that the riding behavior of live aphids is not chance, okay? They actually do control this. Let's look at another example. So river ecology. So 3 species of large fish, A, B, and C, we'll call them, that are native to a certain river have been observed to coexist in roughly equal proportions. A recent random sample of 300 large fish found 89 of species A, 120 of species B, and 91 of species C. Do these data provide evidence that the river's ecosystem has been upset in the sense that these proportions are not what we would expect if the river ecology is normal? So our null hypothesis is that the proportion of A equals proportion of B, which equals proportion of C. The proportion of any one of them should be 1/3. So they all equal each other, right? They're all even. The alternative is that that's not true. So we have three proportions compared. So we have three levels, right, for three species. All of the expected counts are going to be our sample size of n divided by k. So 300 divided by 3, so 100. You would expect if these three species really are present in equal proportions, and you have a sample of 300, you should get on average 100 of each of them. Our degrees of freedom is k minus 1. So we have three species minus 1, so 2 degrees of freedom. Okay. And our chi-square calculation, let me fill this in again, chi-square, okay, equals plus. All right. Okay, so our first calculation is, sorry, I'm not done. Here we go. Our first calculation is for our first species, A. So species A has 89 individuals in the sample. So observed is 89 minus expected of 100 squared divided by expected of 100. That gives you the contribution of species A. This is it right there, 1.21. That's its contribution. Species B, here's the calculation for it. Its contribution is 4.0. Species C, here's its contribution calculation. Contribution is 0.81. You add them all up and you get 6.02. That's our chi-square statistic, okay? Now, let's go take a look at the table. So 6.02 is the chi-square we got to find. All right, so we know we have a degrees of freedom of 2, and so we follow that row down. 6.02 fits between these two values. So we know that our p-value is between 0.025 and 0.05, so we know it's at least somewhat significant. All right, software gives us a p-value of 0.049, so I mean it is just barely significant. If we had a larger sample size, then this would be probably more significant, a smaller p-value than what we actually got. So if our null was true, how likely would it be to find by chance a discrepancy between the observed and expected frequencies yielding a chi-square of 6.02 or greater? 5% or 4.9% chance, basically, right? 4.9% chance, but that's still significant at alpha 0.05. So with this typical significance level of 5%, we would have to conclude the results are significant. We have found evidence, although not extremely strong evidence, that these three fish populations the proportions are not what we would expect, possibly suggesting that there's an imbalance in the ecosystem or maybe pollution or overfishing, who knows what it might be. But we found at least some evidence that these proportions are not what we expect, okay? So what about interpreting the chi-square output? So these individual values, these contribution values that we sum in the chi-square statistic, okay, they're called chi-square components or contributions. And whenever we get a significant p-value, 0.05 or less, let's say, we can look to these chi-square components or contributions to the chi-square statistic and see that the largest components are the ones having the biggest impact or effect on that p-value. These largest components are showing us which of our conditions or levels are the most different from expected. So if you remember, we had for our chi-square statistic, okay, let me just do this real quick. We had the largest component or contribution of 4.0, and we said that was for species B. And so if you plot on a bar chart the percent of total for each of these, you see that species B makes up almost 40% of that sample, whereas A and C are around 30%. And if we are expecting each of them to be 1/3 or 33%, then species B is the one that deviates most from that expectation. We know that because, this contribution, the highest contribution for species B is telling us that, right? It is 4.0 of 6.02 of our chi-square statistic. It's accounting for most of our chi-square statistic. So something's going on with species B, right? Maybe it's out competing the other species, or the other species are being overfished, or who knows, right? But looking at these chi-square components, the contributions can help you tease apart why you have a significant p-value, and you should do that. On Minitab, when you're doing a chi-square analysis, in the test options when you're setting it up, you can tell Minitab in those options to include the chi-square components in your printout, and you should always do that. You should always do that because it allows you to look at this sort of thing and figure out, okay, what level is most out of whack with our expectations, and that can be very insightful. Okay, as the last part of this chapter, let's talk about how to interpret a non-significant p-value. I've said in the past when we've been talking about z-scores and t-tests and things that when you get a non-significant p-value and you have to accept your null hypothesis, we're not saying that the null hypothesis is true. We're not saying that we're proving that null to be true. When you accept your null, all you're really doing is saying, well, you don't have enough evidence to reject it. When, however, you accept the alternative hypothesis, that is a more specific decision. Essentially, you are then saying, yes, we have enough evidence to support this alternative hypothesis, okay? So a non-significant p-value is not conclusive, okay? The null could be true, or maybe it's not true. We don't know necessarily. It just means we probably don't have enough evidence. And this is really relevant with the chi-square test because we're often interested in the null in the sense that it represents a null model of what might be going on. We're interested to see if our data fit a particular model. So a significant p-value is sort of suggesting that our data does not fit a particular model, a genetic model or whatever. But a non-significant p-value, again, is not going to be a validation of the null hypothesis, and it does not suggest that the data do follow the hypothesized model. It only shows that the data are consistent with it. We have to be careful with our wording here, okay? If you accept your null hypothesis, all you can really say is that your data are consistent with that null model. You can't say that they are sort of proving that null model or whatever, okay? Let's look at another example here. So we have chickens called a frizzle fowl. This is a chicken that has curled feathers. You can see a picture of that right there. A genetic crossing between frizzle and leghorn or straight feathered chickens produced chickens in the F1 generation, all with slightly frizzled feathers, okay? Here are the observed counts in F2 by phenotype. So we have frizzled, so frizzled is F, slightly frizzled, which is SF, and straight, which is S, okay? And here are the observed counts of each of those. The most likely genetic model is that of a single gene locus with two codominant alleles, producing a 1:2:1 ratio like I showed you before. So the idea here is that you have your Punnett square, and you have in the F1 parents, they're all going to be codominant for S and F. So these are the alleles in their gametes, okay? So here we would get a chicken, which would have straight feathers, okay? Here we would get a slightly frizzled, I guess they call it. Same thing here. And then here you would get a frizzled, which would be curly feathers. So we have 1/4 straight, 1/2 slightly frizzled, and 1/4 frizzled, okay? So the expected proportions then are going to be 0.25, 0.5, and 0.25. And that's what our null hypothesis here says, right? Frizzled 1/4 or 0.25, slightly frizzled 2/4 or 1/2, 50%, and straight again 1/4, okay? All right, so you see our table down here. This is the kind of table you'll get for as a printout from Minitab. So we have our actual observed counts of each of our three phenotypes. We have our expected proportions under our null hypothesis, and what we need to do is convert those to expected counts. Now, we have a total sample size of 93. So if you take 25%, which you expect to be frizzled, and and multiply that by 93, you get 23.25 individuals. On average is how many you would expect to be frizzled. 0.5 times 93, 46 and a half, slightly frizzled. Again, 0.25 times 93, 23 and a quarter, which would have straight feathers. So these are our expected counts, okay? And we use our null proportions to calculate those based on our sample size. All right, so again, chi-square statistic, okay? Let me just fill all this in. Sorry about the Apple Pencil making the tapping noise, a little bit annoying, but okay. So we do our calculation. So observed minus expected, right? So 23 minus 23 and a quarter. So 23 for frizzled minus 23 and a quarter squared over 23 and a quarter. We do that for slightly frizzled here and for straight here. And you see that we end up with a chi-square statistic of 0.72. Now that's a really low chi-square, okay? So that's going to tell you, again, 0.72, that this is not significant. So we have three different phenotypes. So again, because k minus 1 is our degrees of freedom, we know we have a degrees of freedom of 2. So we want to find 0.72. Well, our first number is 2.77, and they only get larger as you go to the right. So 0.72 is way off over here to the left somewhere. So all we can say about that is that our p-value is greater than 0.25, okay? Because p-values get smaller as we go to the right. Software like Minitab will give you a p-value of 0.698, so 0.70. So this is not significant, right? Our p is greater than our alpha of 0.05, and so we're going to accept that null hypothesis. That means that the differences that we saw in the observed number of chickens of each phenotype versus the expected, those differences are just random variation, okay? That means that our data do fit that particular genetic model. Now, does that mean that genetic model is actually what's going on here in the case of the frizzled fowl? Possibly not. All we can say is that our data do seem to fit that particular model. So we accept that null hypothesis, right? The observed data are consistent with a single gene locus with two codominant alleles, one of Gregor Mendel's genetic models that he developed. All right. So that's how you do a chi-square statistic. And again, these are very useful, but they're used for categorical data. And again, very often you see them with genetic analyses, okay? All right, that's it for chapter 21.